Okay, so a little bit more terminology to talk about in this section. First thing is coterminal. Coterminal is something that it's describing a relationship between two angles. It doesn't make any sense to refer to an angle by itself as being coterminal. It's always a relationship between two angles. So we say that two angles in standard position are called coterminal if they have the same terminal side. Now that doesn't necessarily mean that they're the same angle, even though they look the same, because the coterminal angles can have different degree measures. And the reason for that is because the same terminal side can be thought of as having rotated away from that initial side in a number of different ways. It can be rotated clockwise, it can be rotated counterclockwise, it could have made several full circles before stopping at that position. So all of those would lead to coterminal angles. So to give you an example, a 140 degree angle is coterminal to a negative 220 degree angle. And this image indicates why. Here's a 140 degree angle. Remember, it's measured counterclockwise. A negative 220 degree angle is measured clockwise, but they both lead to the same terminal side, making them coterminal. Now notice also that when you put this arc together with this arc, they complete a full circle. So together it should add up to 360 degrees if we treat that as a positive number. 220 plus 140 is 360 degrees. So there's that 360 degree concept to look for. Okay, so I want to do some examples where we look for coterminal angles, and we're going to do this both in degrees and in radians. So let's start with this one, a 45 degree angle. I want to find two different coterminal angles to 45 degrees. If you think of what a 45 degree angle looks like, it would be an angle that's in the first quadrant, halfway between the positive x and positive y axes. If I have a 45 degree angle here, if I add another 360 degrees to that, it's going to swing me around and take me right back to where I started from. So that's one way of coming up with coterminal angles, adding 360 degrees. 45 plus 360 is 405. So a 405 degree angle would be coterminal to a 45 degree angle. I could add another 360 to that if I wanted to. So 405 plus 360 would be 765 degrees. So these two angles right here and right here are both coterminal to 45 degrees. Okay, so that's a convenient way of doing it. Notice I can keep doing this. There's no reason to stop at 2 other than that's all I was asked to do. But I could just continually add 360 degrees to each angle in this sequence of angles here and keep getting a new angle that's coterminal to 45. Doing this with a negative angle, it's no different really. I can take negative 110 degrees and add 360 to it. That would give me a 250 degree angle. So that would be coterminal to negative 110. One thing I could do that I haven't done yet, I could also subtract 360. And remember, what that's doing is that's taking us from our negative 110 degree angle and doing a full clockwise rotation, but still coming back to that same terminal side. So this would look like negative 470 degrees. Okay. For a question like this, if I gave this question to 10 different people, I could get 10 different answers, because again, I could add 360 any number of times to this, or I could subtract 360 any number of times from this and still get angles that are coterminal to what I started from. So in other words, any given angle has an infinite number of angles that are coterminal to it. It just depends on how many times you want to add or subtract 360 degrees. Now in this case, we're looking at a 4 pi over 3 radian angle. Notice there's no degree symbol. The presence of the pi sort of makes us think that we're looking at radians, but the absence of any word indicating what units we're using means that we're talking about radians. So if I want to work with radian measure, 4 pi over 3, it's not going to work to add 360 because I don't want to mix units. I don't want to add degrees to radians. That doesn't really work. But kind of extending this concept into radians, we still want to think in terms of starting at an angle and then going a full circular rotation to come back to that terminal side. So in this case, with radians, we know that a full circle is 2 pi. Okay, now this is where it becomes really important that you're comfortable working with fractions. How do you add these two? Well, if this were a basic arithmetic class, we would say find a common denominator and then add the numerators, keeping the denominators the same. I am going to jump straight to the answer, 10 pi over 3. That's one of my coterminal angles. Now, if you're not comfortable with where I got this answer without writing out all the steps, by all means, go through the steps of writing out common denominators, but just know that we work with fractions so much in this class that I'm not going to use the time to go through the steps of finding that common denominator and then doing the addition. That's arithmetic, and that should be second nature by now. Kind of sticking with the theme of the last example that we did, this one here, I'm going to try subtracting a full circle. So I'm going to subtract 2 pi. I know that that would also give me a terminal or a coterminal angle to 4 pi over 3. So in this case, this comes out to negative 2 pi over 3. And again, make sure you're comfortable with where I'm getting an answer like that. I'm not showing the common denominators, but you would need to be doing that either in your head or on paper. Okay, negative 9 pi. I want to find some angles that are coterminal to that. This one's easier to work with because, for example, if I add 2 pi to it, I don't need common denominators because we don't have any fractions. This would just be negative 7 pi. I'm going to do something a little bizarre here just to make this one a little more interesting. I'm going to add, not equals, I want to add 100 pi to it. Why would I do that? Well, remember, every time I add 2 pi to an angle, visually what's happening is we're making a full revolution and coming back to that terminal side. So 100 pi is the same thing as if I would have added 2 pi 50 times. Or in other words, this is like starting at a negative 9 pi radian angle and making 50 full revolutions counterclockwise and still coming back to the same terminal side. So this is just a multiple of 2 pi. This gives me 91 pi radians. Okay? And you absolutely do not have to choose a number like that when you're finding coterminal angles, but it makes it a little bit more interesting, I guess. All right, so that's a little bit on coterminal angles. Let's talk about reference angles next. This will become really important soon in Chapter 7 when we're working with sines and cosines. The idea of a reference angle is to associate any given angle with a related acute angle. And if you're rusty on your geometry, an acute angle is any angle that's between 0 and 90 degrees. So the way that we define a reference angle, if t is some angle that's been put in standard position, then the reference angle for t is the acute angle that t forms with the x-axis. And what I mean by that, well, it's easier to see that if we look at some examples here. So if we're in quadrant 1, then the angle is already acute. So the angle is its own reference angle. If we're in quadrant 2, now this kind of didn't print very well, so it's a little bit faded. Let's say that we're in quadrant 2 and we have this angle right here. Okay. Notice that this terminal side also forms an acute angle with the x-axis down here. So whatever this angle is, we would call that the reference angle for t, because that's the acute angle that's formed by that terminal side. There's little formulas down here that show you how to calculate a terminal angle. I would highly recommend against memorizing any of that. It's not a good way to approach this. I would not think in terms of formulas. You want to be able to understand how to come up with this just from the visual. And we'll look at some examples how to do that. Okay. Here, quadrant 2, Oh, we did that one, sorry. Quadrant 3, an angle will be all the way down here. The reference angle is going to be this guy right here. Notice my terminal side is down here, and this is the acute angle that I could form with the x-axis. Quadrant 4 is similar. So let's look at some examples. Determine a reference angle for each of the angles given below. Now for reference angles, any angle only has one reference angle. It's not like coterminal angles where I can just find this infinite list of answers. There's only going to be one answer for each one of these. 81 degrees. We saw in the case of an angle that's in quadrant 1, the angle is its own reference angle. So an 81 degree angle is going to have an 81 degree reference angle. 295 degrees, that's not in the first quadrant. So where is 295 degrees? Well, 295 degrees is more than 90, it's more than 180, it's more than 270, but it's less than 360. It's between 270 and 360, which puts us in the fourth quadrant. Okay, now looking at the fourth quadrant, I like to draw this out. I won't do this for all of these examples, but I'll do it for this one. It's around there somewhere, right? That's the fourth quadrant. So if we're looking at an angle in the fourth quadrant, the reference angle is this guy right there. That's the acute angle that's formed by this terminal side with the x-axis. Now notice if I take the original angle, the 295 degree angle, and then add its reference angle to it, it completes a full circle. So if all I want is this little guy right here, then I could take that full circle, 360 degrees, and subtract off the 295 degree angle, leaving me with a 65 degree angle. That would be my reference angle for this example. Okay? And again, the visual was all I needed. There is a formula right here telling you to do 360 minus whatever angle you have, but I hate using formulas like that. It's much easier to just understand the concept. Pi. What's the reference angle for pi? Well, if you look at pi, remember that's a half circle. Pi radians is that little guy right there. But notice the terminal side is already on the x-axis. It's on the negative x-axis. So there's no positive angle between them. That means that the reference angle in this case is 0 degrees. Okay? You'll encounter that every once in a while. Negative 11 pi over 6. Well, negative 11 pi over 6, where does that live? This is where, again, working with fractions and having some intuition with fractions is really helpful. Think of this as a positive number for a second. 11 pi over 6 is that, compare that to the quadrantal angles. It's definitely more than pi, if I think of this as positive, because pi would be like 6 pi over 6. It seems significantly more than pi. In fact, I think this is almost one full circle, because if this were 12 pi over 6, that would simplify to 2 pi, which is a full circle. So this thing is just shy of a full circle. Now the fact that it's negative means it's being measured clockwise. So if here's my positive x-axis. If I do almost a complete full circle, but not completely, that's going to take me clockwise into the first quadrant. Okay. Now, in this case, yes, we are in the first quadrant, but I measured this angle using something that's negative. Acute angles aren't negative, so I need this last little bit right here. Okay. So if I think of this as 11 pi over 6, how much more do I need to get to 2 pi? Well, if I take 2 pi and subtract 11 pi over 6 from it, I'll get that acute angle, pi over 6. Okay, that would be the reference angle for this example. All right. So I had mentioned before one of the benefits of using radian measure instead of degrees is that it gives us a direct relationship between the angle that we're measuring and the arc of the circle that it subtends. So we're going to use that concept here to come up with some pretty useful formulas. Here, I'm going to be using the letter S to notate arc length. I know that seems like a bizarre choice. You might think, why not use A for arc length? And that's just because A is oftentimes used for some arbitrary constant, or it has other things that we usually reserve A for. It's very common to use S for arc length. Theta is going to represent some angle that we're measuring, and we're thinking of that angle as living in this circle here, so there's theta. It's a central angle, which means the vertex of that angle is the center of the circle, and the radius of this circle will be r. Okay, so our relationship between the arc of a circle and the radius of that circle and the angle subtending that angle, that angle is going to be the arc length divided by the radius. I'm not deriving that here, but it's a straightforward consequence of how we defined radian measure. You do need to be careful with this. This formula assumes that theta is being measured in radians. It doesn't work if we try to measure theta in degrees. Okay? Now, if you solve this for S, multiplying both sides by r, we get this useful formula which can give us the arc length S for some given angle theta and radius r. S is equal to r theta. Okay, so to illustrate what I'm talking about here, let's look at an example. You have a weight that's suspended by a 10 centimeter long string, and it's released, being allowed to swing, kind of like a pendulum. If the string sweeps at an angle of 60 degrees before the weight is caught and stopped, what distance did the weight travel? So imagine that weight and the string it's attached to is being right here. So that's my weight, my little box there. And it's being held up, and then it's dropped, and it's going to swing that direction. Okay? Oh, I kind of smudged that a little bit. Okay? It sweeps out a 60-degree angle right here. And the trajectory of that weight at the end of the string is going to be the arc of a circle. Okay? This little curve would be the arc of a circle if we allowed that thing to rotate completely. So what we're looking for is that length. That's the distance that the weight has traveled. We have enough here to find that. Notice, in order to find the arc length, S, all I need is the radius r and the angle theta, but the angle has to be measured in radians. Okay, so do we have a radius? Well, it doesn't look like a full circle, but if it did complete a full circle, we would see that this string would be the radius of that circle, and it's 10 centimeters. So my arc length should be my angle times my radius. But I can't use 60 degrees for my angle because we need the angle to be in radians for that formula to work. 60 degrees, if you convert that to radians using the conversion method we talked about before, it turns out to be pi over 3 radians. Okay? So my arc length S is equal to pi over 3 times 10. Okay, I wrote theta times r. It says r theta up here, but the order doesn't matter. Simplifying this, whoops, I'm going to get 10 pi over 3. What units of measure do we use here? Well, it's distance. Arc length is like a distance, and we've already been using centimeters for distance, so that's going to be the same units of measure that I use here, 10 pi over 3 centimeters. Okay. The next concept we're going to look at is the area of a sector, but we'll save that for the next video.